a byte variable, which is going to be some kind of input array.
Okay.
And then the call goes into this function that calls a scanf on the string that you type in.
Okay,
which
so
has a format string next to it.
So read is saying that in the phase 2 function, we've got a call, and it calls scanf, and it has a format string which tells it what sort of input to accept. So taking 6%Ds with spaces in between each, and that would be an integer. So trying to find 6 digits to give this thing.
And then there's some relationship between them or on each one that has to be true for it to not explode.
That's right. Okay, so what would be a good name for this function then, Reed?
Read or scan or read 6 integers is what I call it.
Okay. So read 6 ints. If we click X, we'll see it's called again, so it's useful for us to remind ourselves what this function is called. So you should be able to now look at the phase 2 function and figure out what is actually done with these 6 ints.
Have to remember.
Anybody have any questions about x86 syntax, any instructions that are giving you trouble? Okay. Somebody on this side of the room who can tell me what var 4 is for? Anybody figure that out?
Count?
Yeah,
Yes,
just
count.
count. Some count.
Anybody have an equation for how what we're trying to compare?
After the first one, every element of the array should be its index plus 1 times the guy before it.
Okay.
Written on an equation, but this
All right.
math.
Yeah, that's. So we've got some sort of multiplication between the items in your array. So you can see here we've got our counter stored in the ECX. We use that to reference some item in our array, and then we multiply that by EAX, which is our counter plus 1. And then we're doing a comparison with another item in our array. Now, the var 20 thing is kind of it confuses things a bit. And this is actually an artifact of the compiler. So what's happening is your loop starts with 1. Okay. So you see our counter's initialized to 1. So if we had the offset from the base of our array here, so this is our integer array. You haven't figured that out. var1c receives all the integers. So scanf reads in your input, and then it creates 6 integers here. And so here's our first one, second one, third, so on. And our counter starts at 1. So when we multiply that by 4, if we started from var 1c, then this would be the first guy that we'd be addressing in that imul instruction. But we actually want to multiply by the first one. So equation is, so ECX is 1 in our first iteration. And we multiply that by 4. And then we add that to our base. So, so we've got at the minimum, that instruction is going to reference var 1c, and then everything further down the array here. Because as we add, we actually, so this is 0 in our stack, and this is the highest address here. So as we add, we're going to move down the array. But where does var 20 ever get set to something? It's not set to anything. We're not actually, we never, because our counter starts at 1, we never have 0 times 4, which would be var 20 plus 0. Okay.
var 20 is a pointer, right?
What's that?
var 20 is a pointer that's just being, the program's exploding the way the compiler compiles does the variables. So var 20 is just some pointer variable. It's being treated like a pointer.
Right.
So we're only doing offsets from it. We're not actually looking at its value.
That's correct. Yeah. Exactly. So we're adding 1 to that. Yes. Yeah. But it's never pointing at. So we never do something like.
No, it's like we took the address of it. Another.
Yeah, we never do.
Oh, stupid mode effective address.
So var 20 would essentially be var 1c minus 1. So when you do this subtraction, it actually subtracts 4 bytes. So how many have solved this? Okay, so we're doing a loop, right? We're iterating over this list of integers. So we start out with I'm going to call my counter I over here. I equals 1. And we're looping until we get to the counter equaling 6. And we're taking each item in our array here. So we take the first one, and one thing you should have noticed up above is we compare the first item in the array. So this is a dereference. We're saying I want the array, and then I want the value at the beginning of the array. So give me the first integer, compare it with 1. If it's 1, we'll continue on. If not, if this compare instruction is failed, then we'll explode. So we know the first integer. We know that's 1. So we've got that. Then after setting I to 1, we begin our loop. So we say add 1 to EAX, okay? So EAX, I'll just call that A, is 2, okay? And then ECX gets the counter, and it gets the first item in the array. So to me, I don't like the way this is arranged. You know, at least for the first time I'm teaching this to somebody, because really we're saying EVP, the base of the stack, go to the variable var20. Then after that, take our counter, multiply it by 4, and add that distance to our variable. So we're getting our variable and then moving somewhere in that array. All right? And in this case, so ECX is going to be 1. We're going from above our array, one integer above our array. So var20, because this is var1c. So we're starting up here. We're taking our counter and then adding that times 1 to var20. So starting up here, adding the length of 1 integer. Okay. So this is okay. This is a byte. Sorry, this is 4 bytes. So 1 times 4 bytes will bring us to this guy here. Okay, so we get 1, we multiply it by 2, and then we do a comparison with our counter plus, so our counter is going to be our offset once again. We're starting from var1c this time, so we're going to count 1 space ahead. Okay, this would be counting 0 spaces ahead if I wanted this one. This is counting 1 ahead. And that's going to be the result of 1 times 2. So next we increment our counter. I equals 2, means A equals 3. We've got A times the next item in our array. So it's going to be 3 times 2. 6. Increment the counter. Four times 6. 24. And so on. So in the end, we should end up with so in this case, you could write out each of the steps, but let's say you have to calculate hundreds of these. At that point, then you might go to using a script. As long as it's manageable, as long as you have a small number of iterations, you can do it in your head. Then at some point, you might say, well, this is where I can use my Python scripting, my Perl, whatever is the quickest way for you to do these calculations. So I had talked about how this thing takes in an input file. Okay. So go to your directory where you have bomb.exe. Let's create a new file. If you right-click in here, new text file or text document, we'll call it answers.txt. So I recall correctly that our first string was public speaking is very easy with a capital P and a period at the end. And we've got our result from this last phase, phase 2. 1, 2, 6, 24, 120, 720. Okay.
Just a question.
Yeah.
Is there a way to set up like breakpoints to see, oh, how many times you've gone through the loop so you can probably get some patterns down? Because it was easier when you actually did the lab to find that.
Say it again.
So is there a way to set up breakpoints to see how many times you've actually gone through the loop and everything else?
Okay. So you'd like to debug this thing?
Yeah.
Okay. Well, how about this? All right. So, you know what?
Continue on it.
All right. So he brings up a good point. So at this point, this is somewhere where you could use debugging. All right. And one of the catches is that you're going to have to enter the input as it goes. So if everybody's created their answers.txt, save that file, and in our debugger, or in IDA rather, click on the debugger menu. Okay, that's going to bring up a list of options. Here we got process options. So again, this is in the debugger menu. And so we've got application, input file, directory, and parameters. So application is what the debugger is actually going to execute. I don't know how exactly it uses input file, but parameters, a directory is going to be the location where you want it to be executing from. So if you were to open up a command prompt, you were to cd to a particular directory, and then you ran bomb.exe. Let's say you ran it from, you were in the C directory, C:/, and you typed in the full path to get your bomb.exe. You might want to replicate that behavior, so I might remove all this from the directory. And then it would look, when the application was looking for files, it would start in the C directory. But I wanted to actually look for the file where the bomb.exe is. That's where I put my answers.txt. So parameters, you can put in answers.txt. Okay. Now, in order to actually debug this thing, we can put in a breakpoint. So let's say put in a breakpoint right here. Actually, we already know. We know the first item has to be 1. It's the other ones we're concerned about. So we want to know what is being compared. Okay. So add the comparison instruction. Click on that line. Okay. This is the compare EBP plus EDX times 4 plus local var. Once again, this isn't the phase 2. It's the fourth block from the bottom. Click on the second to last line, press F2. That'll highlight the instruction in red, and we can execute. So you can either click Debugger, Start Process, or you can hit F9. And it's going to say, this thing might be malicious. Are you sure you want to run it? Well, we've already run it a few times, so why not? Say yes. And this is one of the artifacts of running in, since we're running in Windows 7, it's actually creating this breakpoint. And Zeno, how about you go sniff out why Windows 7 is doing this to us? All right, so we click OK. It's taking us to somewhere in some NTDLL. NTDLL.dll is a very common. It's used during the load time. It's available to every application that's run within Windows. So it's typically the first thing to be loaded, followed by kernel32.dll. And these things provide the basic functionality that the application needs to talk to the operating system, and it also the NTDLL helps the application load information into the proper memory addresses. Okay. So F9, like it allowed me to start the debugger, it also will let me continue. Now, in this case, it's saying there was a software breakpoint. That was the error that popped up before. And that's because you can see right here, there's an int3 instruction in here. And this is actually why we broke here. So what we'll do here is, this is asking us whether we want IDA to handle the exception, or do we want the application itself to handle the instruction. So if we say yes, the application handles the instruction. It doesn't do anything. It just continues on. This is how a debugger works. When it hits the int3, the operating system gets a signal, and the debugger supersedes the application, so it takes control. Now, an application is just going to ignore that breakpoint instruction. The debugger says, "Oh, we want you to halt." Now, there are, I've actually seen malware out there or legitimate protection schemes for that matter might do this, is they'll actually look through the entire memory space where the code's resident. It will look for CC, which is that byte represents the int3 instruction. And if it notices that in a location where it shouldn't be, it will not act like it's supposed to. So it will either not run the application if it's code protection, or if it's malware, it might try to throw you off the trail. It might try to do something benign and avoid all the fun stuff. So that is why it broke. So
what was the key you pressed to get it to go past the breakpoint and that's how to handle it?
So press F9.
Yeah, that runs it, and you get to the breakpoint.
Yep.
And what do you do at the breakpoint?
So after you clicked OK on the dialog box about the software exception, then you're going to press F9 again. It will bring up that dialog box. It asks you who should handle this exception. Okay. Once you hit yes, it should stop at your breakpoint, assuming that you put one where I did. Now, what we've got here, I talked to you at the beginning about how IDA has this wonderful graph capability. It displays things to you in organized blocks, separated by jump instructions. So any branches, whether they be loops or jump instructions, conditionals. This is the other view. This is the classic view of IDA, and this is what you're going to be dealing with in GDB and OllyDebug. It's complicated to navigate. You can see we've got little arrows on the side here that's showing you this instruction flows into this one here. The graph view, if you have it, why not use it? So with this line selected here, hit the space bar, and it gives us our graph view. Now this isn't always going to work. You might be dealing in code that isn't organized into a function, so this only works within functional code. If you have some shell code, some stub of code that's not defined as a function, you actually will not get this view. It will stay in text view. So it puts our IDA view right on top of everything. If we move this aside here a little bit, you can see, so right here is our live stack. So this is our memory. ESP is pointing here. This is the base of the function. You can see we've got this address here. This is the return value in main. All sorts of information. And then we've got our general registers, okay? And we were interested in comparing our input with what is in EAX. EAX is actually doing the math. So here we can see EAX is 2. So that is the answer we should expect. Now, this is all dependent on your input, right? Because the math to calculate EAX is based on your input. So you would actually have to run the debugger 5 different times to actually get each of those values, right? Because you'd put 1 because we already knew 1 was the
And
first
you just
item.
count how many times it went through.
Right, and then you'd run through and you'd see, okay, 2 is the next one. Then you'd stop the debugger, you'd put 2 in your input, and then so on and so forth. So in this case, it's actually slower to use the debugger. Although in some cases, when you're doing these iterations, it might actually speed things up for you. But
In this case, there was a pattern, so.
right,
So you could, if you were a little sharp, you could detect it.
right. But that being said, you would have to develop some knowledge about what it's doing, right? So either you've already figured out the algorithm because you looked at the assembly and understood it, or you just did it over and over again until you saw the pattern, right?
Is there a way in IDA when you're debugging to edit memory?
Yeah.
Yes. Yeah, you absolutely can edit memory. That is something I'm not going to cover today, but we can talk about it. We'll talk about it outside.
Of course, there was one other breakpoint you had to put, the word boom.
So now we're
But that was when you had to do the lab.
Right.
Because then it actually would go to the server.
Yep. So I'm going to stop the debugger. I already did stop the debugger, actually. So to stop the debugger, there's this big stop button. You can hit Control F2 otherwise. And it's going to bring you to somewhere not so pleasant. So just as we did before, we can jump. We'll go back to the main. And if you are in the text view, which you'll see all these numbers on the side here, this is the address of each instruction. You can see it's the same one over and over again. That's because all this fluff is just comment, and so there's no actual instruction there. When you hit an instruction, that's when you'll see the counter increases here. So if you're in that view, hit spacebar, and you'll get our graph view. And I think now would be a good time to break for lunch.